Okay, so I'm going to talk about ash emissions, and the focus is on some work we did recently on a lean burn GDI, but we developed this ash method about 10 years ago, and we've used it off and on, but I think there's renewed interest in the role of ash. So basically, if we look at why we worry about ash, well, of course, in diesel engines, it builds up and plugs the filter, it increases pressure drop, it increases the frequency of DPF cleaning, and thus also reduces useful life. In gasoline engines, with traditional old three-way catalyst engines, it would plug the passages in the catalyst and lead to catalyst poisoning. Now that we're worried about GDI engines and gasoline particle filters, there's sort of a mixed game with ash. Ash can be good or bad. It turns out an ash membrane increases the GPF efficiency. And so a little bit of ash isn't bad. And also the presence of ash may actually influence the oxidation of soot in the engine, so that's good. On the other hand, it does increase the pressure drop, and so there are trade-offs there. The other thing that's interesting about this ash emission measurement is that we can get a relationship between the ash emissions and engine lube oil consumption. If we look at the nature of ash particles, often the ash particles are decorating the soot. They're stuck to the surface of soot particles. I think actually John Anderson talked a little bit about how the presence of soot tends to suppress the formation of tiny ash particles, and that's because the soot becomes decorated with them. And this shows a decorated soot particle, and then down below we see some ash particles and the elemental composition on various parts of the ash particles. And on the right, we see some size distributions where we found that as you add lube oil to fuel to increase the ash content, the ash or the calcium in the lube oil suppresses soot formation, but eventually with that suppression of soot formation, you get a large nucleation mode forming. So the method we are using is called a high temperature oxidation method. It's originally developed for a study of diesel engine ash. It allows us to estimate oil consumption, but only the atomized portion of the oil is measured here, because the volatile materials, oil evaporation, is not going to really contribute to any of the ash that we see. The method also allows some estimations of the soot reactivity in a relatively quick and easy way. The presentation I'm going to give today will briefly review this method, talk about some traditional applications to diesel, and then look at how this works with the GDI engine, where the only thing we did was change the engine lubricating oil. We didn't change anything else about the engine or fuel, just the lubricating oil. So this basically summarizes the method. You take diluted diesel exhaust, you run it through a quartz tube heated up to 1100 to 1200 degrees C. You then cool the aerosol back down and run it into real-time or near real-time particle instruments. That's the basis of the method. So let's look at some examples. First, considering some diesel examples, looking at soot oxidation, looking at transient ash emissions. So on the plot here, we see on the left, you see we're starting with an aerosol. Here's the number concentration initially. Here's the temperature in the oven going up to a little over 1,000 degrees centigrade. And initially what happens is number concentrations going down. We're eliminating semi-volatile nucleation mode particles here. And then we have a plateau where not much happens. And then we start a steep decrease in concentration. And that's where the soot starts to oxidize. So we're coming down like this. And so we have this behavior. And the mean size of the particles, it goes up a little as you get rid of the semi-volatile nucleation mode. And then it comes down and we end up over here with tiny ash particles and some material out here that we're not sure if it's a residue of decorated soot or some very difficult to oxidize soot. This shows how the method can be used to measure transient ash emissions. So what I have plotted here is the instantaneous number concentration. This is where we're running the oven at 1150 degrees C, so we're just getting what we hope is mainly ash. And you can see here the number concentration. Here's the engine torque. We're running at 150 Newton meters, then we drop to 50 Newton meters, then we ramp up to 500 Newton meters running at constant speed. And you see as you do this upward ramp, you have a very sharp increase in number concentration. So you're getting a puff of ash as we go through this transient, where the piston rings are probably receding. There's probably some oil that's being released as we go through this transient. And then we drop down. There's not much of a transient associated with coming back down to 150 torque. Then we do up ramp again, and we get a smaller spike, but this is a logarithmic scale, so it's not a trivial amount of spike. Then we drop down again. There isn't much of a spike associated with dropping. This jump here is not a spike in concentration due to ash. It's a change in dilution ratio. And then here we have another load jump, and again, a significant spike upwards and overshooting. And again, this is a very large concentration because we're up on a considerably higher scale. Okay, so that's transient work. Here is a summary of what we did with the GDI engine. This is a BMW lean burn naturally aspirated engine. We ran at constant speed and load, 6 bar with a lambda of 1.2. So we're running lean. We ran 3 lube oil packages, one with mainly 5,000 ppm calcium detergent, one with a pure non-anodized polyalpha olefin, and one with 10,000 ppm ZDD-P. This shows the results for the calcium oil, and what you see again here is number concentration coming down. Here is size coming down. Here is temperature. And if we look over here at the size distribution, first few size distributions, not much is happening. Then you get up to about 800 degrees C, and the accumulation mode starts coming down. We come down, burn out the accumulation mode, but then the ash particles coming off the accumulation mode and so on collapse into this nucleation mode. And you get a good solid nucleation mode associated with the calcium additive. The next one is non-additized oil. This is a pure polyalpha olefin oil. And this oil, we see the number decrease is slower and takes a longer period compared to what we saw with calcium. But we get a much greater number decrease. And if you look over on the right, as we go through the size distribution, we come down. Eventually, we form a nucleation mode, but it's a much smaller nucleation mode. And we are not sure where this is coming from. There should be basically no ash in this oil, but we believe it's probably some residue in the sump from the previous test. Excuse me. Fortunately, my sneeze and COVID particles can't penetrate my screen. So anyway, we believe this is due to a little residue because the PAO should not have any significant ash. The next slide shows the zinc additive. And the interesting thing about the zinc additive is this basically shows very, very, very little residue material. And so the question is, even though we're putting in a lot of zinc, we're not getting an ash mode. So what's going on here? Well, that's one of the flaws with this method. Basically, zinc compounds are fairly volatile and unstable, and you can form gaseous zinc compounds in our heating tube. And as a result of that, we basically lose the zinc. And that's why we don't see the formation of this nucleation mode that we did with calcium. So here what I've done is plotted number concentration as a function of oven temperature. And so you can get an estimate of the reactivity of the soot from different sources. So if we look first at the gray curve, this is the calcium additized oil, and you see that starts to oxidize at a relatively low temperature. The oxidation is fast, and you come down to a stable level, which is that calcium ash mode. The next most reactive, and this is mislabeled here, the next most reactive is this curve right here, which is the non-additized PAO. And then the slowest reactivity of the gasoline cases is this zinc additive. And zinc is known to suppress soot oxidation. So this is the slowest reaction. And then finally, even slower is diesel soot. And diesel soot is clearly a lot harder to oxidize than any of the soots we're seeing from the GDI engine. So basically, in conclusion, we see that this high temperature oxidation method lets us make relatively simple measurements of soot reactivity and ash content. The ash emissions are highest for the calcium additive, next for the non-additized oil, and finally for the zinc, where the zinc really doesn't have very much ash emission that comes out in our method because of the volatile compounds. The soot reactivity, again, is highest for the calcium, second for the additized, third for the zinc additive, and even the slowest is the diesel. So that concludes my presentation. Thank you for your attention. Are there any questions? Do we have time?
We do have time. Yes, we have time for at least one anyway. So if anyone wants to raise their hand, please do so.
Johnny, I don't have an ability to raise my hand on this, but wondered if I could ask a question.
Yeah, please do. Yeah.
Yeah. David, nice talk. I wondered, in particular, with your comments about the zinc oxides being hard to measure because they're high, presumably high vapor pressure of an oxide state. Do you think you could correct the method by having, say, a porous diluter? Just presumably you're losing these species by plating out to the walls. And I wonder if you could dilute in a way that cools them down and keeps them from diffusing to the walls. Do you think that would solve the problem kind of with that?
Yeah, I think that definitely would help because they are definitely, these zinc compounds are definitely plating out in the cooling region of the quartz tube. And you can see a white deposit on the tube. So if we could incorporate a diluter for cooling rather than just using convection, I think that would help minimize the loss of these zinc compounds. One thing that's interesting about this quartz tube method is I expected more thermophoretic losses during the cooling than we actually see. We have actually surprisingly low thermophoretic losses, but we believe this is due to the fact that in the quartz tube, as you're heating, you're driving particles away from the wall, and then as you're cooling, they have to make it back towards the wall again. So when you have a poorly mixed aerosol like this, you have a system that doesn't have as much thermophoretic loss as, for example, in a catalytic stripper, where you end up with a rather well-mixed cooling process.
Okay, thank you.
Yeah, I think that's right. Jason Olber might be able to comment as well.
Yeah, Jason has joined us, so he should be there somewhere. He might be trying and unable to speak.
Looks like there's, yeah, a couple questions there, Johnny. Hands raised.
Oh, there are some hand raised. Okay, yeah, Arvin, that's fine. Let me unmute you.
Hello, Dr. Kittelson. This is Arvin from West Virginia University.
I can't hear you very well.
Able to hear me now?
Yeah.
Okay, this is Arvin from West Virginia University.
Yes.
One of my questions is, has any work been done with natural gas exhaust? Because it seems that ash is seems to be an issue with natural gas exhaust, especially in the 10 nanometer range. And it's unclear with what part of that 10 nanometer particles may actually be attributed to lube oil based ash.
It would be a really nice experiment to do. I don't have immediate access to a natural gas engine, but I think it would be a natural for this method. And you could also, experiment with the oil formulations, and you can also look at different oil control strategies. It gives you a quick assessment.
And I think there is, there's also, linking it to the three-way catalyst activity. There seems to be a deterioration in the three-way catalyst activity of aging natural gas vehicles. And from your introduction of this talk, I was just wondering whether that could be attributed to ash deposits in the channels of the three-way catalyst.
Well, certainly the fact that you form these very, very small particles, they're going to diffuse the walls of the three-way cat. And just as that slide I showed illustrated, you really start coating the three-way cat when you have a reasonable amount of ash in the exhaust.
Thank you.
Okay, we have one more question. I think we can just about squeeze that in from Hufang Xiao. If I unmute you, you can speak.
Hi, this is Hui Fan from Afton Chemical. Very nice talk and very interesting findings. So I have two questions. One is about the slide. You show there's the transient ash emission studies where you said there's a spike where it's caused by the dilution ratio change. Can you comment on what's the magnitude of change you are using here?
Could you repeat the last statement?
You said that where you lower the load, but your particle concentration spikes. You said that's not because of the load, is basically because you change the dilution ratio. What's the magnitude you're talking about, the dilution ratio change?
Oh, yes. Here, basically, we went from a single dilution to a double dilution. So you can see, if you look right here, we're talking about a factor of about 25 change in dilution ratio here.
Okay. Okay, good.
So this jump has nothing to do with a transient ash emission. This does.
Mm-hmm. Okay. So it's a factor of 25, you just said, the dilution ratio.
Yeah, the dilution ratio is independent of what we're talking about here. I meant to do a dilution ratio correction when I saw this slide, but had I done that, that would have shifted this whole curve down, and you would have had a continuous line to here, and then the spike. So it's simply a reduction in dilution ratio. We went from double dilution to single dilution.
Okay, thank you.
Okay.
And also quick, on the formulation side, because the calcium and the ZDDP, the concentration you use here is way higher than the typical formulation package. I wonder, when you talk about these, the ranking among soot emissions, between soot emissions, ash emissions and soot reactivity, do you have any recommendation or insights for the formula, like, oil company, for the formulation? How shall we balance that? Because the range you're studying right now, it's higher than the typical treat rate you see in the formulation, the commercial package. What is the balancing point between this ash emission? What is acceptable level? And also, we definitely would like to have a better performance in the soot reduction.
I would probably have that question more for you than for me. But basically, BP gave us these oils just to sort of look at some extreme situations. So this oil we're looking at here is relatively high in calcium. It's basically a calcium detergent. Calcium and magnesium both really tend to form a lot of ash. This non-additized oil, again, here I think the ash mode we see here is a result of just a little contamination in the system. And then with the zinc, this is a very high level of the zinc additive, which of course is a lubricity additive. But the reason we're doing this is that zinc is known to be a sort of negative catalyst in terms of soot reactivity. And that shows up in the fact that in the presence of this large amount of zinc, it's a little bit more difficult to oxidize the soot than it is in the case of the non-additized or the calcium additive.
Oh, okay, thank you. I think we need to move on there. Thank you very much, David.
Okay, I'll stop sharing.
Okay.